Okay, you are live. You can begin now.
Okay.
Good morning, all of you. I welcome everyone on this webinar and thank you for joining us. My name is Dr. Pradeep Kumar Kars and I am working as a assistant professor at the Department of Mechanical Engineering, Paru University. Now, I would like to welcome Dr. Ravi Kumar Jha sir on behalf of Paru University. Welcome, sir.
Thank you. Thank you.
Now, I would like to introduce today's expert. So, Dr. Ravi currently working as a assistant professor in the Department of Aerospace in the at the Hindustan Institute of Technology and Science, Chennai. Prior to this, he was working at School of Engineering, Jawaharlal Nehru University, New Delhi. He earned his doctorate degree in the 2019 from the National Institute of Technology, Silchar, in Mechanical Engineering. He received his master's degree in 2016 from the NIT Silchar in the specialization of design and manufacturing. After getting bachelor degree in the mechanical engineering in 2014 from the Rajasthan Technical University, Kota. He is associate member of Aeronautical Society of India. He has published more than 20 research articles in the patent, SCI and Scopus Index international journals and conference proceedings. His research area are uncertainties quantification, stochasticity in the analysis, computational mechanics, scientific structure, and the functional credit materials. Also, his interest areas in the surrogate modeling. Welcome, sir.
Okay. Thank you, Dr. Kars, for nice introduction.
Welcome, sir.
So we can proceed.
Yes, sir. Sir.
Okay. So we are going to discuss about uncertainties in structure design. So my presentation outline will be very brief, that is introduction and uncertainty in structure design, a case study, and the future outlook. So starting with the introduction, in our title itself, there are two words. One is uncertainty, one is design, structure design. Okay. So first we would introduce about the uncertainty. Uncertainty is the one of the certainty there is, and knowing how to live with insecurity is the one of the security. It is a great scientist, John Egan Follows, said that. So there are four types of uncertainty. One is operational uncertainty, environmental uncertainty, manufacturing uncertainty, and source uncertainty. So in actual, what is source uncertainty? Source uncertainty belongs to the material as well as geometric uncertainty. Operational uncertainty, the uncertainty incorporated with the operation of a particular component, particular machine element. Manufacturing uncertainty inherits from during the manufacturing of the particular machine element or component. We can understood this uncertainty by taking a simple example. So we are, say, consider the bridge over the river. So the uncertainty available in the material from which the bridge is being constructed is the source of uncertainty. The uncertainty which may be induced during the manufacturing, during the construction of the bridge, that is the manufacturing or construction uncertainty. The uncertainty which induced in the operation of the bridge, say the load, that is the operational uncertainty. Environmental uncertainty is the uncertainty which incorporates because of the environment, such as the wind speed, that is the environmental uncertainty. So these are the uncertainty which is quite obvious, it will be there, but it is very difficult to quantify this uncertainty. Until unless we will not quantify this uncertainty, we cannot incorporate this uncertainty in our design analysis. So the contrary to a popular belief, it is a myth that structural engineering design always deal with quantities that are perfectly known. It is a myth that the structure design deals with the quantity that is perfectly known. These are, which we discussed previously, that these are the unknown quantity. So that need to quantify. So there are numerous sources of inherent uncertainty in each design step that are not easily quantifiable. Say for example, in estimating the load, say as we have discussed in case of breeze, the use and occupancy means how much load it will bear. It may vary from time to time. The environment, the uncertainty generated from the environmental origin, that also change from time to time. The wind speed may be at one time 5 meter per second, it may be 100 meter per second, or 1000 kilometer per second also. It depends on time to time. So these are the uncertainty. It is very difficult to quantify, and until we will not quantify, we cannot design a safe and reliable structure. So for better understanding, we can have a simple example of day-to-day life. So when we flip a fair coin, the probability of getting head or tail is 50%. But what happens if there is a soft, muddy floor? It may lead to some possibility wherein the coin will fall neither head nor tail. That is, the coin may fall vertical, right? So in such case, the the general understanding that the probability of getting head or tail is 50%, it may be wrong. Apart from this, the manufacturing uncertainty is the coin may not be perfectly unbiased, also deviate the outcome from the general expectation. We are considering that there is no uncertainty in the manufacturing. The coin is unbiased, but it is not correct. It may be biased because of the manufacturing inaccuracy. So this may also deviate the outcome of the expectation. All the physical or mathematical model are formulated based on certain boundary condition, as we have discussed previously, that we have some certain assumptions that the manufacturing has been done. There is no error in the manufacturing. It is unbiased coin, so that the outcome will be 50%. There is no the floor is tough. There is no muddy floor. So these are the boundary conditions. So all the physical and mathematical model are formulated based on the certain boundary condition and assumptions, which are often not strictly valid. So the uncertainty in prediction increases as we go away from the present moment towards the past or future. As we can see from this figure, that this is the present moment. As we goes away from the past and future, the uncertainty prediction increases. In day-to-day life, we can see that we can observe the uncertainty in movement of particles such as atoms, molecules, occurrence of events, incidents, birth, death, accident, these all are uncertain. Winning of game, any action, reaction in our biological system, our human behavior, our activities, all are uncertain. So this is a great challenge to quantify this uncertainty. It may be our day-to-day. The program belongs to our day-to-day, or it may belongs to our engineering system. So in engineering system, the programs is failure analysis, stability analysis, static and dynamic analysis. All these type of analysis is required for safety of the structure. As most of the structure nowadays is being manufactured with the help of composite. So composite are exhaustively used in windmill, construction, marine, aerospace industry, sports, everywhere, in high-speed vehicles. either racing cars, anywhere. So most of the structures are nowadays made of composites. And due to its inherent complex manufacturing process, it has lots of scope of uncertainty. So if there is uncertainty in their source, in the material, in the fabrication process, in manufacturing process, then obviously there will be their global response on their analysis also. So we need to study these analysis: failure analysis, stability analysis, impact analysis, static and dynamic analysis, buckling analysis, in the light of uncertainty available in the manufacturing. So as laminated composites are often used in various functionally important structures such as aircraft, it is important to quantify the uncertainties associated with the response of the structure. Say, one may ask how we can say these composites are being used in most of the structures. So even for example, if we consider the aeroplane Airbus A380, more than 50% of the structure is made up of composite. We can see from this figure, starting from the radome, nose landing gear, thereafter wing, bulkhead, stabilizer, tail cone, spoiler, everywhere you can see these components are made of composite. Now it may vary. That's a composite. There are different types of composite: laminated composite, sandwich composite, functional integrated composite. So depending upon the types of application, different types of composite is being used. But overall composite application is more than 50% in aerospace industry. Now from this figure, we can see this is our real system. Okay, we can see this figure. I think this cursor is visible to you. Yeah. So uncertainty in time history, uncertainty in the location. This is the input: earthquake, turbulence. Thereafter some system uncertainty, parametric uncertainty, model uncertainty, calibration uncertainty. So the total uncertainty consists of input uncertainty plus system uncertainty plus computational uncertainty. So all these three uncertainty, input plus system plus computational uncertainty, will be incorporated. So in the computation is being used. Computation will be done by finite element method, and that is from that computation we will get some model output that will be further validated with the experimental one. This is the whole outline of the uncertainty quantification, how we are being employed in our computational analysis, and that is further validated with the experimental result. Okay, so we can replicate this uncertainty propagation with a tree approach. This is a tree. This is the root of the tree. The root of the tree is replicated with the source of uncertainty. This source of uncertainty, as we are pouring the water in the root, that is going throughout the leaves. So the source of uncertainty, that is the root of the tree, is propagated to all the leaves. So what are the leaves? These are the leaves which is very important for a structural design point of view. That is a failure analysis, static damage, dynamic analysis, harvesting analysis, bending analysis, dynamic elastic properties, stability, impact. All these type of analysis is being done for the design point of view of any structure. Since nowadays we are using a composite structure, so we are focusing on the composites, not on the monolithic material. Okay, so this tree replicates the our uncertainty quantification, uncertainty propagation approach. So now we are concentrating on the sandwich plate. Composites having different types of, so here in the sandwich plate, we are using the laminated composite as the face sheet, and in between two face sheet, upper and lower face sheet, we are using the core. Core may be soft core, it may be honeycomb or any other structure. Okay, so these are the core which is in between the two face sheet, upper and lower face sheet. So this sandwich structure is analogous to the I-beam. In basic solid mechanics, we have all of us have studied that economic structure where we are replacing the square or circular structure with the I-beam or T-beam or triangle. So there where why we are using I structure instead of a square, because from the relation of bending formula that sigma by I square y by I, from that bending formula there is a scope of rearranging the material, keeping the height same, so that the moment of inertia, area moment of inertia can be increased, and as the area moment of inertia increase, the resistance to bending will also increase. So the here sandwich structure is also analogous to the I-beam, where flange is represented by the face sheet and this wave is represented by the core. Okay, so the most of the load is being carried by the face sheet. In the solid mechanics, we have studied that the maximum load is being at the outer and innermost fiber, whereas the in between fibers getting the low load. So we are replacing this regular square with the I-beam. So here's the same analogy we are applying to manufacture the sandwich plate. So here in the face sheet, we are different lamina is there. So different lamina comprises of the face sheet, and thereafter the soft this core is there, and this upper face sheet, lower face sheet, and core is being fixed up with the adhesive layer. Thereafter, this is a final fabricated sandwich panel. So why sandwich plate? So steel plate or any of the monolithic plate. So as per the DIAB guideline, so for the same span length, the same load, 1000 Newton per meter squared, and the same span length of 1.5 meters. The weight carrying capacity, the diffraction in the steel plate is 30 mm. Diffraction in the sandwich plate is 30 mm. Okay, but the weight of the sandwich panel is only 4.3. That is almost 1/10th part of the weight of the steel plate, that is 39 kg per meter square. And the factor of safety which is available in the steel plate is 3. That is of in the sandwich plate is 5.7. It is double of the monolithic material. So as the core thickness increases, the stiffness of the sandwich plate increases exponentially, whereas the weight of the sandwich panel increases linearly. We can see from this figure, for 80% increment in the core thickness, only the weight is increased by less than 5%, whereas the stiffness is increased by more than 40%. So as the core thickness will increase, our sandwich panel will be more stiffer. So how this sandwich panel, how this sandwich plate impacts in lower environmental impact? Because it reduces the weight. As the weight will reduce, the requirement of the engine will be small, and since this is this composites is not thermal conductive, so we do not require the additional insulation. So it also reduces the additional structural requirement for the insulation, and by the reducing the weight, the fuel consumption will also reduce. By reducing the fuel consumption and requirement of the lesser amount of material, the impact on the environment will be less. Now the next is uncertainties in the structural design, a case study. So here we are considering a sandwich plate wherein we will discuss how the uncertainty is being incorporated in the sandwich plate for the buckling analysis. So buckling analysis of sandwich plate in the stochastic rhythm, that is the uncertainty quantification rhythm. So here the objective of this case study is to establish the importance of higher order buckling mode. Importance of higher order buckling mode. In deterministic approach, normally we are using the uh, single critical eigenvalue for means single buckling mode, whereas it is important to consider higher order buckling mode in case of a stochastic analysis. The next objective is to analyze the effect of different end condition, means different boundary condition, whether it is simply supported, clamp or free, whatever it is. The next objective is to determine the effect of stochasticity in material and geometric properties, and to find the effect of other parameters such as the ply orientation angle, core thickness, facet thickness, and number of laminates. So how we will start uncertainty quantification approach? So first, identification and definition of stochastic input parameter. What are the input parameters where uncertainty is being available? That uncertainty parameters need to be identified. Thereafter, formulation and development of original simulation model to obtain buckling load of sandwich plate. Then we will consider some design point for obtaining buckling load corresponding to each design point using the original simulation model. Once we are getting the buckling load for original simulation model, we will go for surrogate model validation and formulation. Thereafter, Monte Carlo simulation using surrogate model. Once we will get the Monte Carlo simulation for all the parameters, we will go for the characterization, statistical analysis, and the interpretation of result. So there is well-known approach for probabilistic analysis that is named as the Monte Carlo simulation. But there are some drawback in Monte Carlo simulation, that is that it is quite extensive approach, means it is quite computationally extensive, it is quite time consuming approach. So in order to reduce the computational time without affecting the accuracy of the result, we are coupling the original finite element approach, original MCS model, with the ANN model. What is ANN? ANN is the artificial neural network. Artificial neural network, as our brain works, this ANN also works. How? Say we are having, today is temperature is 40 degrees Celsius, tomorrow is, yesterday was 39, day before yesterday was 38. So we can predict tomorrow temperature also, it will be nearby 41, 42 temperature degrees Celsius temperature. So by seeing the data, 10, 20, 50 data, we can predict how will be the next. In the similar fashion, similar to our biological brain, this NN also works. They are also analyzing the data and they are predicting how will be the future. So here in NN there are inputs, there are input layers, hidden layers, and outputs. So there are some segregation that is given by some weight to the hidden layer, and we are getting the output some prediction is there. So as per our brain, brain is also defining some data, and thereafter they are predicting. Here also these input and hidden layers are defining the data and giving and doing the prediction. So the first step is validation of finite element analysis and the area analysis. So we have considered a sandwich plate of 10 centimeter length, 10 centimeter width, and 1 centimeter thickness. And for that, we have done the validation from the previous literature. And from this table, we can see that it is in it is in convergence with the previous literature. So in case of probabilistic analysis, two types of validation is required. One is finite element validation, and second one is surrogate model validation. So here, first we have done the finite element validation. Thereafter, we will do the surrogate model validation. How we are doing the surrogate model validation? For surrogate model validation, surrogate is nothing. It is the ANN, artificial neural network. Okay. So here we are giving different samples to the ANN, such as 64, 128, and 256. We have given four samples: 64, 128, 256, and 512. We have given these four samples to the ANN model. Thereafter, these ANN model have given the prediction for the 10,000 number of samples. Because in original Monte Carlo simulation approach, we are taking 10,000 number of random samples. So we want to get the prediction of 10,000 number of samples by giving 64 number of samples to the ANN. So what the ANN is doing, ANN has analyzed the 64 data sample, and they have predicted for the 10,000 number of samples. Like that, 128 to 56 and 512. So we can observe that for 500 0%, about 0.1%. Okay. So from this,
Sir.
am I audible?
Yes, sir. Your screen is not visible, sir.
Screen not visible.
Yes, sir.
Now?
No, sir, not visible.
Now it's okay?
No, sir, not visible, sir. Please share the screen. First stop the screen, sharing of screen, then share this.
Okay.
Share.
Okay. Now it's okay?
Yes, now it is visible. Now open your presentation. Yes.
Done?
Yes, now visible.
So here from this figure, we can see that for 512 number of samples, the ANN is giving the best result, having the percentage error less than 0.001%. So we can consider this 512 number of samples for the further analysis. So, so for surrogate model validation, we are doing the PDF probability density function as well as the scatter plot. So from PDF also, this green color represents the result obtained from the Monte Carlo simulation approach, whereas this different color source for different number of samples: 64, 128, 256, and 512 number of samples. So we can see this 512 number of sample plot is closest to the MCS result. Okay, in all three cases, this is for the first buckling load, second buckling load, and third buckling load. Okay, for CCCC boundary condition, that is the clamp boundary condition. Okay, so this is the scatter plot with the NN model with the original finite element model, that is the MCS model. MCS, so original finite element model means the result obtained from the direct MCS approach, and NN model means the result obtained from the NN approach. Okay, NN model. This is for 64 number of sample, 128 to 56 and 502 number of sample. So we can observe that as the number of sample is increasing, the diversion from the diagonal is decreasing. So this for 512 number of sample, the diversion from the diagonal is minimum, and from the previous study we have also observed that for 512 number of sample, the error is minimum, that is less than 0.001%. So from this analysis, we can consider the 512 number of samples for further analysis. So here we have coupled the NN surrogate model with the finite element model in order to have the computational efficiency without affecting the accuracy. Okay. So we are considering the important. We have our first objective was to importance of higher order working mode. So why it is important? We can see here. If we can consider only first buckling mode, then what will happen? The second and third buckling mode is also overlapping. So there is a chance of failure in second and third buckling mode also. So it is important to consider the higher order of buckling mode while doing the uncertainty quantification, while doing the stochastic analysis. This result shows for the CCCC boundary condition, SCSC, that is the where C for cramp, S for simply supported, F for free end. Okay. In this case, in this CFCF, it is not required to consider the higher order working mode, as there is no overlapping zone. This figure represents the effect of degree of stochasticity. As the degree of stochasticity increases from 10% to 20 to 30%, the overlapping zone increases. Here, this figure represents the effect of ply orientation angle, that is 30 degree and 60 degree, and this is the number of lamina. So for here CCCC boundary condition, in case of number of lamina, the first and second buckling mode is overlapping, and in case of CCCC boundary condition for 30 degree and 60 degree, both case first buckling load and second buckling load is overlapping. This is the effect of core material property on the overlapping zone. So here also the first, second, and third, both buckling mode is overlapping in case of CCC boundary condition, whereas SCSC boundary condition, the first buckling mode is not overlapping with the second buckling mode. So we can say that it is quite important to consider the higher order buckling mode in case of realistic real application. So we can see that these are the different parametric study for the different say ply orientation angle, core thickness, number of layers. This figure represents for the different number of layers. For 8 number of lamina, 12 number of lamina, 16 number of lamina, how this overlapping zones come into picture. This is for different material property. The first one for Scott ply 1002, and second one for the S glass epoxy. So now the sensitivity analysis is being conducted in order to assess the importance of different input parameters on the overall response of the structure. So from the sensitivity analysis, we can see this TC is the core thickness and PC is the core material property. This core thickness is the most prominent parameter, most important parameters which plays a vital role in the overall response of the structure, whereas the ply orientation angle theta is the least prominent parameter which plays a least importance in the overall response of the structure. Right? So here we can say this is for the CCC boundary condition, this is for the CFCF boundary condition. So irrespective of the boundary condition, either it is CCCC or CFCF, irrespective of the boundary condition, the the core thickness TC is the most important parameter. As we have discussed in the introduction part itself, as the core thickness increases, the stiffness of the plate will increase. So the core thickness is the most important parameter in the global response of the structure. Okay. Here this figure represents for the SCSC boundary condition and SSS boundary condition. Here also the core thickness plays a vital role, and the ply orientation angle theta is the least important, right? So the conclusion is the bottom-up Monte Carlo simulation based non-intrusive uncertainty quantification for buckling analysis of laminated soft core sandwich plate is presented. So bottom up approach means we are considering the uncertainty as the input which is propagating from the source to the overall structure. Initial input level to the overall structure. So that is the bottom up, starting from the bottom to the top. Okay. So complete prognostic description of the first three buckling load for various crucial factors related to boundary condition, ply angle, material properties are shown for individual and compound effect of source uncertainty based on an efficient surrogate based approach, that is coupled NNFE approach, which is having the significant level of computational time and cost saving potential. We have seen that the higher order buckling mode is having quite important. Why? Because an intriguing outcome of the prognostic result for buckling load is the realization of the importance of higher order buckling mode due to the existence of overlapping zone among the different eigenvalue. If we have considered only the first eigenvalue as the critical, then there is a chance of failure when for the second or third buckling, because it may possible that second eigenvalue is more critical than the first eigenvalue. So it is important to consider the higher order buckling modes. Okay. So in a deterministic analysis, normally a single critical buckling load is considered corresponding to the minimum eigenvalue. However, it is shown previously that there exists a non-unique critical buckling mode in case of a stochastic analysis when the inevitable source uncertainty are accounted. In the previous analysis, it is shown that the existence of overlapping zone and the area of overlapping depend on the degree of uncertainty. As the degree of uncertainty increases, the overlapping zone will increase. Okay, so it is the overlapping zone and the area of overlapping depends on the degree of uncertainty in the input parameters, boundary conditions, and structure and material details. So we need to consider high order buckling mode by keeping into mind all these things: input parameters, boundary conditions, structure, and material details. By using the ANN based ANN coupled finite element approach, significant level of computational efficiency of more than 19 times is achieved without affecting the accuracy. Accuracy is also achieved more than 99.9%, as the error is less than 0.001%. The prognostic result shown here shows that inevitable effect of source uncertainty has significant effect on the impact response of the sandwich structure as well. Thus, it is important to adopt inclusive design approach by considering the probabilistic variation of the global response in ensuring adequate safety and serviceability. The future outlook. Even though numerical results for the first three buckling modes is presented here, but certain problems with high level of source uncertainty may require analyzing even higher modes, right? Future research could be carried out to quantify the probability and subsequent reliability analysis for the possibility of the occurrence of such overlapping zones based on the respective overlapping area involved. Various other buckling sensitive lightweight structures can be investigated concerning the higher order buckling modes following the efficient surrogate based approach. Variability in manufacturing and operational uncertainty can be considered. Here, in the present case study, we have considered only the source effect of source uncertainty. We have not considered the effect of manufacturing and operational uncertainty. That may be considered in the future study. The hybrid simulation approach adopted in this study. What is the hybrid simulation approach? That is the NN coupled finite element approach adopted in this study to achieve computational efficiency in the expensive and time-consuming process of modeling the complex structural forms like sandwich structure with composite face sheet can be useful for other computationally intensive problem of structural analysis and mechanics. In future, other surrogate model, there are different surrogate models such as ANN artificial neural network, PNN polynomial neural network, RBF, radial basis function, Mars, multi-adaptive regression spline, SVM, several surrogate models are there that can be coupled with the MCS for the better computational efficiency and can be employed for complex structure in order to assess the effect of uncertainty on the overall response of the structure. Thank you, everyone. Any query, any question, please?
Thank you so much, Dr. Ravi Kumar, for giving your valuable knowledge to our PG scholars and the faculties about this interesting topic. We appreciate you for making a time in your busy schedule. Thank you again. Dear participants, if you have any doubt, any query, you can ask here.
Yes, please.
If you have any doubt, any query regarding this webinar, you can ask here. Otherwise, you can also mail your queries to Dr. Ravi Kumar, and he will definitely reply you. Okay, sir. I think there is no queries. Thank you again, sir, for joining this webinar and giving your valuable times. Thank you again.
Okay, thank you. Thank you, everyone, for giving the opportunity for delivering a expert talk. Thank you, everyone. Thank you for bearing with me.
Dear attendees, I will share the feedback link in your Gmail. Okay. And kindly respond that feedback form. Based on that, I will give the participation certificate. Thank you again for joining this webinar. Now you will leave.